Alright students, so we are now going to discuss about the next periodic property, which is the ionization energy. So the next topic that we are starting is the ionization energy. Let us just quickly define this and then we'll see its trends along the period as well as down the group. So ionization energy is the amount of energy required to lose an electron from the outermost, or that outermost is known as the valence shell, the outermost or the valence shell of an, very important thing, of an isolated neutral gaseous atom. So this is the definition of the ionization energy. The amount of energy which is required or which is absorbed by that shell in order to lose the electron. So amount of energy required to lose an electron from the outermost or valence shell of an isolated neutral gaseous atom. So what does this mean? If there is an element is a pure form which is consisting of the similar type of the atoms. The atoms, they are having inter-atomic forces of attraction. So if I want to isolate one atom, so I'll have to convert it into the gaseous state. In the gaseous state, the forces of attraction will be decreased and the atoms will get separated out. So in that form, we can get an isolated gaseous atom. And atom is neutral in nature. So we get isolated neutral gaseous atom. And in that isolated neutral gaseous atom, from that atom we are going to lose an electron. Alright? From where? From the outermost or the valence shell. So the amount of energy which is required to lose an electron from the outermost or valence shell of an isolated neutral gaseous atom. This atom will absorb this energy, and by absorbing that energy it will be going to lose its electron. Now, this ionization energy is always measured in positive value. So, it is always in the positive value. Why? Because it is absorbed by that atom. Required means that is requiring that energy, that is absorbing that energy. So, absorbing energy by an atom is always given to be as positive. Alright, so this ionization energy will be always having its positive value. What are its units? The SI units, because it is energy, it will be in the form of joules, but mostly it is represented in kilojoule per mole. It is represented, its SI unit is kilojoule per mole. It is the form of energy, but it is calculated per mole. Or the other unit would be, other unit is electrovolt per atom. So the other unit would be electrovolt per atom. So SI units is kilojoule per mole. The other unit would be EV, that is electron volt per atom. So this was all about the ionization energy. What is this? How much energy is required to make this atom lose its electrons from the outermost shell? That is what the ionization energy. It is always positive. And its SI unit is kilojoule per mole, other unit would be EV per atom or electron volt per atom. Now we'll discuss its trends along the period as well as down the group. So we'll discuss that trend now. Alright, so for that concept of the ionization energy, let us discuss one thing, or let we understand this one more time. Ionization energy is the amount of energy which is absorbed by that isolated gaseous atom so that the electron will be lost from them. Now, if an atom is having a very huge size and the nuclear pull is very less, so it will easily remove its electron, means the ionization energy would be less. In the other case, if the atom is having a smaller size and the greater nuclear pull, So it means it is difficult to remove that electron from the outermost shell. So for that, the value of the ionization energy would be more. By taking this concept, now we'll discuss their trends. So let us just discuss its trend first down the group. So let us first discuss the concept down the group. So less ionization energy would be for that case that can easily donate the electron. The more ionization energy will be for that atoms for which it is difficult to lose that electron. Alright. So let us see its trend and we'll take the example of the first group as always, alkali metals. So it is Halina, Ki, Rubina, say friendship. So francium will give the radioactive value, so we'll not consider that. So this is how it is. So again we are writing their atomic number. It is 1, 3, 11, 19 and so on. Electronic configuration, we can also write it as 1, 2, 1, 2, 8, 1, 2, 8, 8, 1. So as we have discussed, down the group atomic size increases and down the group nuclear pull decreases. So out of these all group, for cesium, it is having the biggest size. So it is having the biggest size out of these all and least nuclear pull. Out of these all atoms, this cesium is biggest in size and it is having least nuclear pull. Which means for cesium, if this is the nucleus, there are numerous shells surrounding it and outermost shell is far away. Outermost shell is very, very away from the nucleus and thus there will be a high screening effect. So the nuclear pull will decrease. If nuclear pull will decrease, atomic size will increase. Because of less nuclear pull, this means this electron is not in the strong forces of attraction towards nucleus. So it means the attraction is very less, so it can be easily lost from the atom. It can be easily lost from the atom, forming CS1 positive. That is the cation, unipositive cation. So out of these things, cesium is biggest in size and least nuclear pull. So it is easier to lose this electron. Now let us consider this with hydrogen. Hydrogen is having only one shell which is very, very close to this nucleus and there are no screening electrons, so nuclear pull will be maximum. Size is very small. So it means it is in a greater nuclear pull. So in order to lose the electron, in order to make it to lose electron, it would be difficult as compared to cesium. Alright. So for hydrogen, it is difficult to lose. For cesium, it is very, very easy to lose. So it means out of these two, which will require a higher ionization energy? Hydrogen, because it is difficult to remove and we want to remove, so we'll give a greater amount of energy to this. So hydrogen is having a great ionization energy as compared to cesium. So what can we say? That down the group, the ionization energy decreases. So down the group, ionization energy decreases on the account of their greater size and lesser nuclear pull. So it will be easier to lose the electron. We require lesser amount of energy. So for hydrogen, great ionization energy. For cesium, very less ionization energy. So it means down the group, the ionization energy decreases. Alright, so ionization energy decreases down the group. Now let us see its trend along the period. So the next thing or the next trend that we are going to see is the trend of ionization energy along the period. So again, it will be dependent upon the atomic size and nuclear pull. We will take the example of the period 2. In period 2, we are having lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Alright, so this is 3, 4, 5, 6, 7, 8 and 9. Again, let us just write down the electronic configuration 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. So, as we move along the period, the screening electron remains the same, but the protons are going to increase. Nuclear pull, effective nuclear charge will be going to increase, and along the period, the atomic size decreases. So, fluorine is having the smallest size. So this is the smallest size. And in this, if active nuclear charge is maximum, so nuclear charge is maximum. Nuclear charge is very, very high. Alright. So it means if the nuclear charge is very, very high, let me just make a diagrammatical view. This is the nucleus, and the outermost electron is in a stronger pull towards the nucleus. The outermost electron is in the stronger pull towards the nucleus. So it is difficult to remove this electron because it is in a strong nuclear pull, because effective nuclear charge is very, very high and it is smaller in size. Now let us just go towards lithium. Lithium is having a greater size. So the size is higher as compared to fluorine, because we know along the period size decreases. So this is on the left hand side. So it means it is having the greater size. So it is bigger in size, and nuclear charge is less, and less nuclear charge. If the nuclear charge is less, it means it is not in a strong influence towards the nucleus. So we can easily remove this electron. So it means it is easier to remove this electron as compared to this. So fluorine requires more ionization energy to remove the electron. This is easier to remove. So it will require less energy to get removed. So we can say along the period ionization energy increases. So along the period ionization energy increases. For fluorine it would be maximum in this case, and for the lithium it would be minimum. So ionization energy increases along the period and decreases down the group. Alright. So this trend is always not like this. There are some exceptions. Those exceptions we'll discuss in a completely or entirely different video, so that we can revise these things also, and we'll discuss all the exceptions about the atomic size, ionization energy, electronegativity, electron affinity. We'll discuss all the exceptions. There are exceptions for almost each and every case. For that we'll make a different video and we'll discuss all that in that video. So in general, along the period ionization energy increases and down the group it decreases. So again, if this is the ionization energy, we'll take the case along the period it will increase and down the group it will decrease. So again, ionization energy is the another periodic property. It increases on one side, that is along the period, and decreases down the group. It means ionization energy is again a complementary form. That is, if it increases on one side, it will be going to decrease. So ionization energy is also complementary in periods as well as in groups. So this was all about the ionization energy. Energy required to make an atom lose its electron, but it is always in the isolated neutral gaseous form. Alright. So ionization energy is measured in kilojoules per mole or electrovolt per atom. So this was its trend along the period as well as down the group. In the next video, we'll discuss about the next periodic property, which is electron affinity or electron gain enthalpy.